We've talked about how computers are based on binary, the base 2 number system, which consists of either 0 or 1, and the reason for that is because computers are based on electric circuits, and electricity has two states, off or on. Each binary digit is a bit, meaning it's one place that can either be off or on, so 0 or 1. One single bit is the smallest unit of information processed by a computer. However, we typically look at bytes when we look at computer memory. One byte is equal to 8 adjacent bits, so that means we have 8 bits that are next to one another. You've most likely heard of the byte before. Your phone might have 64 gigabytes of storage space, your laptop might have 8 gigabytes of RAM, your flash drive might have 16 gigabytes of storage, you might have 10 gigabytes of photos in your iCloud account. A gigabyte is 1 billion bytes, and that's the byte we're talking about now. Your computer's memory, or RAM, is just a huge sequence of bytes. A byte's location in memory is its address. So here in this diagram, we have a sequence of bytes, and if you notice, each byte has 8 binary digits, or 8 bits, that it's made up of, so this memory location number 3 is just made up of the 8 bits 0, 1, 0, 0, 1, 0, 0, 0, and altogether that makes up just 1 byte. But how do we represent this location in memory? Well, it's actually rather simple. If you have 8 gigabytes of RAM on your computer, that means there's 8 billion bytes. Each byte has its own memory address, so that means there's 8 billion addresses. We number each adjacent byte in memory by just counting. We start from 0 and then we go all the way to 8 billion minus 1. The minus 1 is because we started counting from 0 and not 1. If we had only 32 megabytes of RAM, we'd only have 32 million bytes and our addresses would go from 0 to 32 million minus 1. So that's simple enough. Based on how much memory space you have that much bytes, and each one of those bytes has its own address. A sequence of bytes, so a group of bytes one after another, can be used to store a number, a string of characters, a picture, a sound, a video, a program instruction, a CPU instruction, basically whatever you need it to store. The amount of bytes in memory it takes up depends on how big that number or string or picture is. For example, on your phone you might have a couple thousand text messages that are being stored, but since those are just text, it doesn't take up that much space. Maybe it's like 300 or 400 megabytes. If you have a couple thousand pictures stored on your phone, that's a lot different. That might be taking up a couple gigabytes, maybe 7 or 8 gigabytes. The reason for that is because text requires a smaller amount of storage space, so a smaller amount of bytes in memory, than a picture does. Okay, so our memory is composed of a sequence of bytes, and each byte, or each memory location, has an address to identify it. When the CPU gives instructions, it refers to these memory addresses, and these addresses are just the sequential number of that byte in memory. Index registers in the CPU are used to help calculate the address in memory, or a specified instruction or operand. So let's take a look at some examples of how we can store different types of data. Let's say I want to store just a single number. To keep it simple, let's store an integer, meaning a number without any decimals. Let's say I wanted to store the integer 19. Well, computers store things in binary, so I need to convert this number into binary. Let's see how many places we need. The process for converting any base 10 number to binary is basically just breaking it down into the powers of 2 that make it up. The largest power of 2 that fits inside of 19 is 2 to the 4th, equals, 16, so we need to put a 1 in the 2 to the 4th spot, and let me go ahead and draw this out. So we need a 4, 3, 2, 1, and 0 spots. Okay, so I mark a 1 in the 2 to the 4th spot to represent the 16, and now what's left? Well, it's just that 19 minus 16, so the 3. What's the biggest power of 2 that fits inside of 3? Well, that's just 2 to the 1st, or 2. Let's mark that spot, and now what's left? Well, 3 minus 2 leaves 1, so just 1, and 2 to the 0 equals 1, well, that'll cover that. So let's mark that as well. So there we go, we have 16 plus 2 plus 1, which is 19, and since we don't want anything else, we put zeros in all the empty spaces, so 19 in binary is 10011. This has 5 spots, so it'll take up 5 bits. 1 byte is 8 bits, so this number will fit inside of 1 byte. If I had to store a bigger integer, let's say 2018, in binary that's 1111110010, and that's 11 bits, which is more than 8, so I need at least 2 bytes, or 2 memory locations to store it. How big can we go? Well, that depends on the data type we're using to store these numbers. We'll get into the different data types later, but for now, just know that we store integers in binary in our computer's memory. So storing integer numbers is Easy, but what about the numbers that have decimals, like 12.5 or 3.1415? Numbers with decimals are called floating point numbers, and storing them in memory is a little more complicated. It also uses binary, but it's a special notation called the mantissa exponent notation. We'll cover that in a separate video so we can spend some extra time on it. Okay, so we store numbers in memory by just converting them to binary for integers or using a special binary notation for floating point numbers. But what about letters and characters? We can't do a mathematical conversion to change the letter R to a binary number. Instead, we just use a standard code to encode our letters into numbers. This is basically just a big table that says this character is represented as this binary number. One of the most popular codes is ASCII, or the American Standard Code for Information Interchange. Here's the table for ASCII. So, notice that this encodes not just letters, but also symbols like these guys, and even spaces. Also notice that the letters themselves are coded twice, once for the uppercase version, and then again for the lowercase version. You might be a little confused on why numbers are in here, but this is a character number, so if I was storing, for example, the string Welcome to Classroom 12A, the 1 and 2 are being used as characters in a string of characters, so we code them based on ASCII, not their ordinary binary equivalents. If that's confusing, don't worry. It'll make a lot more sense when we look at strings. Okay, so this is ASCII, but Java uses a code called Unicode, which uses 16 bits or 2 bytes to represent each character. The first chunk of Unicode just duplicates the ASCII encoding pattern, but then it has a lot more room to encode other characters and even other alphabets. So that's how we store characters, by encoding them in a number based off of ASCII or Unicode, and then storing that number in binary. If I wanted to store a string of characters, it's basically just storing one character after another. We'll get into the details of strings later, but just keep in mind that they're quite literally just a string of characters put together. When it comes to storing sound, images, and video in computer memory, it's a little more complicated since we're basically taking something analog, meaning it has a continuous range of infinitely many values, and then sampling it frequently enough to get a binary representation that's a good enough replication of the original. I won't get into the details of storing sound, images, and video this time, but at the end of the day, it's still just being stored as bytes in memory. If we think about it in a sort of big picture way, it really is incredible that we've created machines which are built off of the simple two states of off or on, or 0 and 1, and we've been able to create billions of those bits and bytes so that they can store information in our computer's memory. Whether it's numbers, characters, strings, images, video, it's all stored as sequences of bytes in our computer's memory.